Welcome. Tuesday, bright early Tuesday morning. So really appreciate you being here. We'll go ahead and kind of kick this thing off because obviously we know we all got stuff to do today. So I'm gonna try to give you a little bit of brain cram first thing in the morning, get you some information, and then digest it. And then obviously if there's any questions at the end or even down the road, definitely get in touch with Brody or us, and we'll do what we can do to help you out. Okay, so let's get started. There's this whole new buzz about Wi-Fi. I should say it's funny that I say new buzz because Wi-Fi is not new, but there's this new buzz about Wi-Fi in the building automation market, and we got to make sure that we talk about it and get really from a conceptual standpoint to understand how this is going to work. Okay, so first things first, let's go from super. Let's pull back 50,000 feet and let's talk about it. Okay, so let's talk wireless, right? Because a lot of times people say, "Well, I want wireless." Okay, well, what the heck does that actually mean? All right. So when we talk wireless, there's all different types of wireless communications out there, and here are just some of them that we typically deal with, or that from a day-to-day standpoint, or even in our industry right now. So we got Wi-Fi, we got InOcean, Zigbee, Z-Wave, Bluetooth, NFC, and there's lots and lots of other stuff out there. Okay. So when you start looking at implementing some type of a wireless system, it's really easy to get confused because there are so many choices. Okay, I mean, what do I want to go with? Do I want to go with the Z-Wave? Do I want to go with the Zigbee? Do I want to go with some type of a new Bluetooth implementation? Do I want to do this? I don't know, right? So the first thing you got to do is, again, you got to step back and you got to think about it, and you got to say, okay, well, what's my application going to actually need? All right, so let's look at some things to start with from a wireless standpoint. Okay, some of the issues we like to call them common issues. So number one, do you have an understanding of that wireless technology? So if you get an RFP or an RFQ that says, hey, I want you to implement this type of wireless system. Do you understand why that wireless protocol? Do you understand Zigbee? Do you understand Z-Wave or Notion or whatever it is? Or if you're going to a direct bid style solution, um, are you comfortable enough putting in some type of a wireless system? So make sure you have the understanding. Okay. Number two, poor wireless choices. So even though we have a lot of those wireless, I just showed you a lot of different choices for wireless, it doesn't mean that they're good for our industry. So if you look at it, like for instance, I put for poor wireless choices, we have Zigbee and Notion. Now there's a reason I have that, and that reason is because those are not adopted widespread. So Zigbee um, is very isolated to our market and the home automation market. So there's a great thermostat manufacturer out there that's been doing Zigbee for years. I'm not going to put the name in. You all know who I'm talking about. They got a very nice solution. But if you come outside of that one manufacturer's thermostat solution, who else is doing anything with Zigbee? Not very many people. Now, in the home automation market, it's a little bit different. There's light switches, there's outlets, there's water leak detection, there's all that type of stuff. And quite honestly, I use that personally in my home automation. So Zigbee's great in home. Now, would I ever implement that into a commercial building personally? No, I would not. Um, and we'll talk about why you would choose certain things going on here in a minute. One of the biggest factors of that is usually with the Enotions, with the Zigbees, with the Z-Wave, the range is very poor. I was actually a little conservative here and said usually it's right around less than 50 feet. That depends. So if you do line of sight, you can probably get close to 100 foot, but realistically, if you put one thing in the way, that power transmission of those protocols is so light and so weak that it drops usually to around 15, 30, maybe 50 feet. So, which again, in a home atmosphere, that's fine. But if you look at an office building where one office to the next office is probably every bit of 75 to 150 foot away, it doesn't really work that well. Depending on the protocol, you'll have a lack of redundancy. So if you go with something like an Ocean or something like that, you won't have any type of a mesh. Sorry, I can't talk this morning, everybody. Mesh solution. So there is no self-healing properties or that type of stuff. And then use of centralized versus distributed architecture. That means is there some type of a main brain box that has to deal with that communication, like a gateway. So if I wanted to take something like an ocean communication protocol and bring that back to something else, I have to have some type of a gateway that converts that wireless in ocean to something and then gets it connected to something else, okay? So that would be centralized. And then on top of that, obviously, with the centralized versus distributed, you start talking about, am I cloud-based doing something versus localized-based or on-premise? So you can get kind of deep into that as well. When you're looking at doing any type of a wireless solution, you have to do a site survey. There's no ifs, ands, or buts, okay? Because just because you walk into a building and they have something, whether it's Wi-Fi or Zigbee or Z-Wave, that doesn't mean it's going to work for you where you want it to work. So you have to do a site survey, okay? And a lack of a site survey is basically setting you up to fail. And we'll talk more about site surveys later in the presentation. And then that last one there is always the big push that we're seeing more and more with networks, and that is network security or improper network security, lack thereof. So depending on the protocol, do they have network security built in? So when we start dealing and you start thinking about all of this stuff, you got to come up with an idea of what you want to use. Okay, so here's what EasyIO did. EasyIO basically said, all right, we're going to look at all these different wireless communications and we're going to pick what we think is the best, okay? So one of those that we talked about was Z-Wave. Again, Z-Wave is a very good wireless mesh communication protocol that is perfect for home automation. Would I ever use it in a commercial application? The answer is absolutely not. Because of the lack of, number one, devices that utilize it, because the signal strength is not very powerful, that I can't get the distances that I need, I would not suggest using that. Can you? Yes. I've seen people actually do it, use Z-Wave in a very, very small commercial building, and there's adverse effects. Some people say, oh, it works okay. Some people are like, man, to get it to work, I had to add all these other repeaters so I can actually get the signal to where I need it to go, and so on and so forth. Okay? All right. Let's go with the next one. We talked about Zigbee. Again, Zigbee, it's been around for many, many years, specifically in the HVAC market with that specific thermostat manufacturer. And does it work? Yeah, it does. It works fine. But there's limitations on the distance. There's limitations on how many devices can connect back to a specific or a single gateway, and you have to have a gateway to get it to communicate to anything else. So if I wanted to communicate BACnet or something like that, I basically have to take that Zigbee communication protocol. I have to convert that over to BACnet with a gateway that is not cheap, and then put that into my IP infrastructure. So would I suggest using that? Depends on your application. Did EasyIO adopt that? The answer is no, we did not. So when we started looking at all of this stuff in the industry, and we said, okay, what's the most commonly used wireless communication protocol out there? So we had our answer. And then from a manufacturer standpoint, we also had to look at it as, instead of having to design a chip that is specific to some protocol and put that onto ours, what can we as a hardware manufacturer be able to source and not break the bank and then pass those costs on to you, our customer? So we looked at it, and the most prevalent wireless communication protocol out there, guys, is, ding, 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 it's Wi-Fi. So we chose to go with a Wi-Fi solution, okay? And here's the reason. Wi-Fi is everywhere, and we all know that. You can go to a McDonald's, you can go to a Panera Bread, you can go to a Starbucks, you can go to basically anywhere, and you'll see a sign that says free Wi-Fi. So Wi-Fi is everywhere. So since it's everywhere, EasyIO's stance was, okay, we want to use something that everybody is already using. That way we don't have to reinvent this chip. We don't have to reinvent this technology. Everybody is relatively comfortable with it. So that's what we're going to go with. So because Wi-Fi is out everywhere, let's go ahead and implement that into our controllers and see how we can make our buildings smarter. Okay? All right, so let's talk about how we can, what are some applications for Wi-Fi enabled devices. So again, the plan here is I'm starting from a very, very high conceptual level of Wi-Fi, everybody. Once we get down to that, then I'm going to drop into our controllers. We'll talk about our controllers and some network design architecture and stuff like that. But we have to understand the fundamental layer of communication that we're going to be using before we say, okay, yeah, here's my controller, go use it. That's where you could set yourself up to fail, okay? So, applications for Wi-Fi enabled devices. Single site edge controller, data aggregator, modernizing equipment for data logging. You could do RTUs, residential and hotel applications, and then we can integrate via BACnet IP for metering, billing, and centralized data collection. So what does all that mean? Basically, that means the whole move in our industry, the building automation industry, the temperature control industry, the controls industry, whatever you want to call the stuff that we work in from a day-to-day, is there's this thing that I call IP convergence. And all of our stuff is moving to that IP layer or the IT network. Serial bus communication is going away. All right, I equate this, or I kind of give the analogy of, in your home, do you still have an analog modem, like a 56K modem? And everybody goes, no, absolutely not. That's ridiculous, right? Well, guess what? That's what serial bus communication is. Serial bus communication at its fastest is going to talk at 70,000 baud, 76.8 or 78.6, whatever, right? So that's slow. That's slightly faster than a 56K modem. So in our homes, we have broadband modems, whether it's, Spectrum, Time Warner, Cox Media, insert your brand here. It's fast. We're talking typically 100 megabit download speeds. Some people actually have fiber optics run to their house now. So at our home level, we're getting smarter, faster, and more up to date. But at our building levels, we're still not. From that mentality, we're still going to go in and put that serial bus communication. That's like if somebody came to your house again and said, okay, I'm going to put this internet in your house, and here's this 56K modem. And you're like, oh, that's great. Yeah, no problem. No, we can't deal with that anymore, guys. So we have to be smarter, and we have to come into this world where we're going to be dealing with IT personnel, okay, which means we have to be comfortable, we have to understand it, we have to get the knowledge we need so we can understand how to talk with these people so we can live together cohesively, okay? So we got this IP convergence. Everything's moving to this IP network. I mean, you're seeing it more and more with rooftop unit manufacturers and metering applications where it's like, oh yeah, we're BACnet IP, or we're doing this, or we're Web API, or whatever, right? So everything's going IP. So like I mentioned a second ago, a key thing is we have to make sure we understand what we're doing. It's just like when we started in the industry and we started running that serial bus wire, whether it was LawnWorks, Modbus, BACnet, or some legacy proprietary. We had to understand how to do it, right? I understand I got to run from this to this, but can I change polarity? Do I have to put end-of-line resistors? Do I have to do biasing? Okay, what's the maximum length? All of that stuff that we inherently know about serial bus, we now need to learn and understand about IP networks. Now, the nice thing is, IP networks, in my opinion, from that standpoint, is much easier. Where it gets more difficult is actually when you have to get into configuring network switches and all that. But guess what? That's not our business. If we get in touch with the network person first and we become, quote-unquote friends with them, at least we're not enemies, let's put it that way, then we can work with them very cohesively to come out with a very, very good solution, okay? So we need to make sure we understand what we're doing. So knowledge is power. So there's online classes you can take. You can hire network professionals to assist you for gaining that knowledge, whether that's hiring them full-time or maybe, hey, I'm going to go do my first implementation of an IP network or a Wi-Fi network. Sub it out. Contact some local IT group, work with them, say, hey, we want you to do this for us, and then just hang out with them while they're doing their job. I mean, you don't need to sit there and watch them pull wire. We get that. Okay, maybe you watch them pull one or two wires. Okay, got it. But then when you're talking about doing site surveys and just kind of hang out with them and see what they're doing so you can gain that knowledge. It's like back in the day where you were an apprentice and you're watching your journeyman do work. Same type of idea, right? Our good old friend YouTube. YouTube has the answers for almost everything. Whether you want to change out something on your garage door, rebuild an engine, or learn something about Wi-Fi networks, YouTube has it. Obviously, one I forgot to put on there is our best friend Google. You can also just Google things. Go to Google, put in something, and you'll get a million different results of how to do it. So we have to make sure we get the knowledge that we need. Okay? So hopefully some of this, like these little Tech Tuesdays that Brody puts on, they're awesome because that does provide you additional knowledge. Okay? And hopefully I'm going to help out with some of that very, very base level knowledge for Wi-Fi networks. All right, so let's start very, very top at the, again, basics. So let's talk about what Wi-Fi truly is, okay? Wi-Fi is a communication standard created by the IEEE. The IEEE is the Institute of Electrical and Electronic Engineers. What does that mean? Super smart people, way smarter than the person that's talking right now, okay? So they came out with this communication protocol and said, here's how it is, here's how it's going to work, and this is it. Boom, okay? And it's called 802.11. Now, there are different versions of 802.11. So if you happen to have gone to buy a new router recently, if you went to Best Buy or whatever, you will see that it's a G, N, AC or something like that. Those are different implementations of the 802.11 standard. And it basically boils down to speed and distance. Okay, in the actual spectrum that they're on as well. So the funny thing is, I was actually doing a little bit of research here recently on Wi-Fi, and it feels like Wi-Fi's been around for 100 years. But realistically, the base standard was created back in 1997. So it's only been around for around, realistically, if you look at it, 1997, it's 2019, so not that long, realistically. So it came out in 1997. The B version of the implementation came out in 1999. The G version, which is probably a little more prevalent, we may see a little bit more about, came out in 2003, so realistically 4 years later. And then the N standard, which is probably the latest and greatest that we see a lot of from a mass-produced, widely spread. That would be the N. N as in Nancy, that came out in 2009, which was 6 years later after G. And then probably the latest one out right now that is not so popular, it's called AC. That came out in 2013. That's where you typically have these routers that have, 6 antennas on it that basically look like little spaceships. So that came out in 2013. It's called AC. There's a new one expected to come out later this year called AX. So again, just like everything in the industry, there's constant improvements happening. So there's going to be new hardware, there's new software and firmware that's part of these hardwares that are coming out. So expect a new version AX out in the late versions of 2019. Okay. All right. So let's talk about the frequencies. Frequencies are just different spectrums that these devices communicate on. So you got 2.4, you got 5, and you got 6 gigahertz, which is going to be coming part of that AX, from my understanding. So those are the 3 most popular right now in a standard commercial home environment. 2.4 and 5 gigahertz are the standard. EasyIO, what we've done is we've implemented our controllers with 2.4 gigahertz. The reason we've done that is you have better penetration power than the 5 gigahertz. 5 gigahertz is faster, yes, but we're not streaming Netflix across our controller. We don't need that speed. We actually need the penetration to go through the walls and wiring and so on and so forth. 5 gigahertz does not have that power to go through. Okay. Wi-Fi is a low power radio frequency, so RF. So when you really think about it, when I think of radio frequencies, I think of like the radio station in my car or something like that. Those are super, super high power, right? Ours is not. Or Wi-Fi is not. So it's a very, very low power. So depending on lab environments and so on and so forth, line of sight, you could probably get anywhere to 300 to 500 foot line of sight. When you start putting things in the way, you're probably talking more about, let's call it, maybe about 150 foot, somewhere around that. But you don't know until you start doing site surveys. Notice I keep hitting on site surveys. I'm going to keep hitting on it as we go through this presentation. Okay? All right. So now that we kind of understand it's a communication standard, okay, what's the next thing? Okay. So next thing is, what do we need to make this thing work? Pretty simple. You need to have some type of a wireless transmitter. That's going to take internet data or some type of data communication and convert that over to a wireless signal. That's typically going to be like a router, a hub, or an access point. Now, a lot of times people think routers and access points are the same thing, and they're not. An access point is typically something that's taking a hardwired internet connection that's part of a network, and then it converts it over to a wireless signal or a Wi-Fi signal. Whereas in a router, actually does all of that, but more. It actually routes data, and it can convert. It does like DHCP addressing. It can do port forwarding. It can do all that stuff. Where an AP does not. AP is a very simple, dumb device. I hate to say dumb. A simple device that takes that hardwire connection on the internet or network and then converts it over to a wireless. Okay. And then you need some type of wireless receiver. That could be a laptop, a phone, a tablet, smart TV. It could be a Roku, or it could be, guess what? Ding, ding, ding. It could be a building automation controller, right? So, pretty simple when it comes to that. All right. Hopefully everybody understands some of that. Now let's get on to the next thing, and let's start talking about some vocabulary and terms. Okay. So, WLAN, that's a wireless local area network. So basically that is the area that a wireless transmitter signal can be received. So you may have heard the term LAN before. So when you take it and put a W in front of it, it's just, hey, here's what the wireless signal can reach, and here's what so when I connect to an access point or a router, I'm part of that WLAN. Okay. Network, I don't typically say WLAN or even LAN anymore. I always just say the very generic term called network, because as a network, that's some sort of infrastructure used for data transfer. That could be a WLAN, that could be a LAN, that could be realistically serial bus if we want to go back 1,000 years. So there's that type of stuff. It's just some way to transmit some data. Okay. All right. Let's do a little bit more vocabulary. So now we're going to get a little bit nerdier, guys. So I talked about access point a little bit. That's some type of a hardware device that allows other Wi-Fi devices to connect to a network. Like I mentioned, hardwired to wireless. Client, very simple. This is some type of device that connects to a Wi-Fi network. Let's talk about the nerdy stuff now. So we got a thing called an SSID. This is our service set identifier. Basically, that's the name of the Wi-Fi. So when you go to do a scan, that's the name of that access point or that network or that router or whatever that you're going to try to connect to. And you'll see multiple ones out there. So that's what that SSID is. All right, there's a thing called DBM or DBMW. Depends on how, basically, whichever one you want to use. They're synonymous. But what it is, it's a measurement of power loss in decimals using 1 milliwatt at the reference point. So I want you to think about it this way, okay? If anybody by chance would happen to be like an electrician from trade earlier, it's the same thing as voltage loss. So decibel milliwatts is a loss of power from the origination point to the destination point. So when I have my router sitting there, it's going to put out 1 milliwatt of power. And the farther I get away from that access point with my phone or my tablet or my whatever, that power signal is going to drop. So if I'm 10 foot away, let's say it's 10% or 90% signal, so I lost 10%. And then I go 20 foot away and I lost another 10%. And then I go 100 foot away and I lost 70%. As you can see, it just makes sense, right? The farther away I'm from the source, the less the power I get at my client or end device, right? So let's equate that to power loss. So again, if you're an electrician, let's say you have a 14 gauge wire and you put 120 volts through that wire, and that wire is 10 foot long. At the end of it, you're going to read it and it's going to be 120 volts, no problem. Now, if you take that exact same 14 gauge wire, the exact same 120 volt power, and you run that wire 1,400 feet, you will not have 120 volts at the end. You will have something less just because you get that voltage loss through that copper conductors. It's the same thing. Okay, so dBm is a measurement of loss of signal strength. Okay, and it's always going to be like negative. It'll be something like negative 60 dB, negative 40 dB, negative 90 dB, or something like that. Now, to the common person, that's not really that doesn't mean much to me. Like if I see a negative 67 dB, does that mean a whole lot to me? Typically not. Nobody understands in what I would call the real world what that means. So what we've done is we've created this thing called an RSSI. Not we, EasyIO. I should say the standard, the IEEE. They created this thing called the RSSI, which is a received signal strength indicator. Now, that's an estimated measurement of power level that the RF device is receiving from the AP or router. So from the client device, the end device, what's that signal strength? And then I put it into a number. Now this is a scaled value based on dBm signal loss. So for instance, if I'm 20 foot away from my access point and my dBm is negative 47, that's going to equate to an RSSI of something like 75% or 80%, something like that. Now, those numbers mean something to me. When I know that 100% is good and I know that 50% is not as good, right? So when I start looking at that, that means something. So the bigger the number on the RSI, the better the signal strength. On the dBm, the greater the loss. So when I go negative 100, that is horrible signal strength. Negative 30, the less loss, is great. I hope that makes sense because I'm looking at negatives at that point, right? Because I'm actually doing signal loss. Okay, moving on. Let's talk about this is kind of RSSI, and here's how it works. So I think we're all familiar with those type of things. You know, if you look at it even from a mobile standpoint, hey, I got 4 bars or whatever. This is the same type of thing. When you look at it, even on your computer, you'll have these bars that show you whether you have good, bad, or indifferent signal strength. And that's kind of what this picture, this icon equates to an RSSI. Okay. Now, it's kind of tough to see here, but down underneath it, there are some negative dB signal strengths on the presentation there. A little tough to see, so that's why I wanted to kind of give you this one. So this one kind of equates a little bit differently. So so if you look at the negative dBs there, so negative 30 dBm, that basically equates to 100%. Negative 52 dB is 80%, negative 89 dB is 10%, and negative 110 is 0%. So basically horrible. So as you can see here, the greater the loss, the more negative, the less signal strength you have is RSSI. Okay? All right, moving on to this one. Just a different way to show it. So this kind of tells you, so now that I understand the negative dBs a little bit, and now I understand a little bit of the RSSIs, let's actually look at what this means. So negative 30, that is a phenomenal signal strength. That basically means you are right on top of that router. You got the best signal you can get. And that's not typical in the real world because you're going to have some distance away. But let's call it anywhere from a negative, realistically, negative 40 to negative 65. That is a phenomenal signal strength, okay? Anything from, let's call it negative 67 to approximately negative 69, negative 70 is still very, very good. That's where you want to be when you're doing streaming video, so you're not getting, signal degradation from Netflix or whatever, or you're doing a VoIP system or something like that. Okay, negative 70 still okay. That's where you can do email and web surfing, no problem. Probably not the best to do, YouTube streaming and Netflix streaming. So they will kind of degrade the signal down from, the maximum resolution to something less. And then as you start getting lower and lower, negative 80, negative 90, that's really not great at all. You probably have very spotty connections. You may actually drop in and out and so on and so forth. Okay, so stuff that's really important to know, right? Maybe you knew some of this, maybe you didn't, but this hopefully is going to help you out. All right, let's keep going to the nerd stuff. All right, so there's a thing with Wi-Fi stuff called channels. So channels are essentially paths for data to flow. So I like to think of them as like lanes on a highway. So if I have a network, whether it's a building or what, an office building, my home, whatever, I want to make sure that I'm getting data flowing as fast as possible. So that's where channels come into the world, okay? So let's take a look at something here so I can kind of get you guys really kind of nerded out. And what are you showing me, Brian? All right, so essentially this is what the channel stuff looks like. In the United States, we are allowed to use channels 1 through 11. Channels 12 and 13 get added on for the rest of the world, and you notice you got channel 14 way over there off to the right-hand side. So the only area in the world that can use channel 14 is Japan. Don't know why they're so special, but they are. So basically, in the United States, we have 1 through 11. That's what we're allowed to use, okay? And to kind of nerd out a little bit, essentially what happens is you have a spectrum of basically for this whole spectrum, you have 100 megahertz. So from 2.4 gigahertz to 2.5 gigahertz for everything, okay? And then what happens is when you look at these channels 1 through 11, or realistically 1 through 13 if you want to add those two in, but let's not. Let's just stay 1 through 11 because that's what we use in the United States. The channel centers, so basically the top of that arc between 1 and 2 and 3 and 4, every one of those is 5 megahertz apart. Okay, so from 1 to 2, that's 5 megahertz. Now, the crazy thing is that each one of these channels is 20 megahertz wide. So if you look at it, channel 1 is 20 megahertz, channel 2 is 20 megahertz, channel 3 is 20, and so on and so forth. But the center of the channel itself is 5 megahertz apart, and there's 11 channels. So what happens is you get what's called channel overlap, and that's what you're seeing with all these little arcs and colors and all that stuff, okay? Now, when you look at channel 1 and channel 2, for instance, channel 1 is overlapped by channel 2, and channel 2 is overlapped by channel 1 by approximately 70%. All right? That's not what we want. We do not want to have channel overlap. So if you ever do any Googling on channel stuff on the web or whatever, it says channel 1, 6, and 11 are the 3 channels that don't overlap. Now, that's kind of a misnomer because they absolutely do overlap. They are just the ones that overlap the least amount. Okay, so if you look at 1, 6, and 11, they actually don't touch each other, right? So, but if you look at, like, for instance, if you go to 1, 2, and 3, those all touch multiple things going both ways. So anytime you're in the networking stuff when it comes to Wi-Fi, everybody says use channels 1, 6, and 11. No problem. Got it. Not smart enough to really understand why. That's the way I look at it. I'm like, okay, that's what they tell me. I look at it, I still see overlap, but okay, I get it. All right, so these are the ones that overlap the least. Okay, so then they're saying 1, 6, and 11 are the ones I need. Cool. Now, because the way my brain works, guys, is I kind of need to make sure I understand why it works. So let's look at this. This is kind of the way the channels work in a very, very dumbed down version. This is what I needed. So let's say, go back to the days when you were in gym class or something like that, back in elementary school and middle school and whatever. And you're in gym class and your teacher says, all right, everybody go out there and spread your arms out and you make sure you're not touching the person next to you, right? And of course, you and your buddy get right next to each other to where like your elbows are touching each other. And now your teacher says, okay, do jumping jacks. All right, so then at that point, you're slamming into each other and all that. That's kind of the way that it boils down with the channel stuff. So if you look at 1, 4, 6, 8, and 11, if all of those in the top one, if everybody started doing jumping jacks, I'm going to start hitting each other, right? But if I come down to the bottom section, and if I'm only using 1, 6, and 11, 1, 6, and 11 have plenty of room to do their jumping jacks without smacking into each other, okay? So that's called adjacent channel collision, basically. All right? So the idea is you want to make sure that you are on an open channel as much as possible. So when we go to do these site surveys, you're going to look at your channels. I'm going to show you some stuff here in a little bit, but you're going to look at your channels and you're going to say, okay, which channels are the most populated? And you may see a lot of stuff on channel 6. Now, does that mean you should not be on channel 6? Not necessarily, because you can do co-channel, the word I'm looking for, co-channel, I'm sorry, it's early in the morning. It's not co-channel interference, but basically you can do co-channel stuff to where everybody's on the same channel. And what happens is, even though you're on the same channel, you do have added traffic, so you'll have a little bit of latency, but it works a lot better than having a bunch of stuff on channel 6 and you hop on channel 5. And the reason being is because when you're on channel 5 and there's a bunch of stuff on channel 6, that's that adjacent channel interference. And essentially, there's no way for the networks to kind of work together. So as you're sitting there trying to talk on the network on channel 5, channel 6 is trying to talk on the network as well. So you basically get into a big screaming match. So think about it this way. So let's say you're at a rock concert, or you're at a bar, or you're, back, even let's say you're in a class or something, and you start talking with your friend and everything's fine. But then more people start showing up, and then they start talking. So you have to start talking louder, which means they start talking louder because they're trying to talk over you. And you talk louder, and they talk louder, and it just becomes a big, big, nasty shouting fit. So that's basically what happens when you're doing adjacent channel interference. So even though there might be a lot of stuff on 1, 6, and 11, it's probably better to hop on those than to get right next to another one. So let's say 1's really busy, 2 and 3 are open, 6 is really busy, 7, 8, 9, 10, and 11 are open. So what would I go on? Well, in that case, I'd probably go on 11 because it's open. But let's say 11's crowded. So then I would look at 1, 6, and 11 and figure out which one's the least crowded and probably hop on one of those so I don't get the adjacent channel interference, okay? All right, so I'm going to kind of take it out of the nerdness now. Let's come back a little bit, and let's just go to some common stuff. So what interferes with Wi-Fi? Lots of things, everybody. I think we kind of know this, but I really got to put it out there. So concrete, brick, rebar, steel, elevators, stairwells, satellite dishes, power sources, heavy machinery, cordless phones, wireless video, wireless speakers, RF radio signals, monitors, LCDs, microwave ovens, chicken wire, believe it or not, tinted windows, neighboring Wi-Fi devices, Wi-Fi sensors, Bluetooth devices, snow, and rain. Now, you may not have thought about some of this, but I actually was doing a little, like I said, I was doing a little bit of research a little while ago, and there was a really, really cool thing where somebody had an access point and a site survey spectrum analyzer, and they were looking at the signal wave. They turned on a microwave, and the signal went crazy. The reason being is because a microwave uses 2.4 gigahertz just like we do. So the way that the specification's written is that the microwave signal is allowed to bother us, but we cannot bother the microwave. Kind of strange, but that's just the way it is. So what it boils down to here is all of this stuff becomes interference because it's something in the path. It's that simple. So is something in the way of where my access point or my transmitter is communicating to my receiver. All right. Now, the last two on there, snow and rain, people don't think about. So if you go to do an outside installation or something, and you do remote mount antennas, and you're on a rooftop, and you're like, man, this should work no problem. I'm going to stretch it out really far to where my signal strength's only around 60%, but that should be okay. Well, it'll be okay until you get a downpour. Because once you get a downpour, that rain will block the RF signal strength, and you will have problems. It's just the way it is, okay? So stuff to kind of keep in mind. All right, site survey. Okay, very, 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 very super important. Anytime you implement a wireless solution, I don't care if it's Wi-Fi, Zigbee, Z-Wave, and Ocean, I don't care. If you're doing some type of wireless, you need to make sure that you do a site survey. So here's some of the things you needed to do. Okay, I'll make sure that I provide this to Brody. Brody, you guys can pass that out to everybody on this call to make sure they have a copy of it. I believe Frank also mentioned to me that we're recording this, so you'll have access to that as well. But essentially, the steps for doing a site survey. I'll tell you, you can do this if you want to yourself. If you want to get into that market and you want to actually do it, I suggest investing in the software, investing in the knowledge to do it. If you're not planning on doing it and you're like, man, this is something it's over my head, then all you have to do is go find a network company, sub them out to do a wireless site survey. They'd be more than happy to take your money to do this, I promise you. And when they're done taking your money, they're going to provide you a report and say, here's your dead spots, here's where you need to put access points, here's what you're doing, this, that, and the other thing, okay? So this is the key things. You got to do this, you got to do 1, 2, 3, 4, and 5, all right? I'm not going to go through and read them all, but essentially, you're going to put an access point, you're going to walk around, you're going to scan the network to see where you have dead spots, all right? Go to the farthest area. You're basically going to find your boundary, of how far you can go out. Once you find that, you're going to come back inside of that boundary, and you're going to walk around some more and make sure you don't have any dead spots. Now, You can't do this. If you're going to be implementing some type of a building automation system where the controllers are above the ceiling, don't expect to walk around at ground level and get a good signal and say, okay, this is going to work, because guess what? Your signal strength is going to be different above a ceiling. You have ductwork, you have conduit, you have lighting fixtures, you have all this stuff above a ceiling that's going to impair the wireless signal. So a site survey is in depth. It's not just walking around with your phone and an access point going, oh yeah, I can get to this room, I can get to that room. No, that's not enough. You actually have to pop ceiling tiles, see what signal strength is, and so on and so forth, okay? Now, as far as the site survey software tools, there's many of them out there. You can actually Google those up. But a couple of them that we've dealt with in the past, there's one called WiSpy, WISPY. InSSIder is what. So Insider, InSSIDER. That's probably the one that I've seen the most personally. There's NetStumbler and there's Air Magnet. But there's a bunch of them out there, guys. So you just got to go look, find one that you like. You can start off with some freeware. Some of them have free trials to see if it's what you like. The nice thing about them is you can actually do something with like a heat map. So it kind of looks like that. Basically, this is an Air Magnet. So basically, you import a digital floor plan. You put an access point somewhere, and you start walking around, and basically you're hitting buttons saying, okay, here's my signal strength, da-da-da-da-da. So it becomes a heat map. So obviously green good, yellow not so good, and then as you get farther and farther away, you'll get into reds, and reds obviously really bad, okay? So this is something you have to do when you're doing a wireless installation. No ifs, ands, or buts. You have to make sure you know what your communication looks like, okay? All right. So for our stuff, a site survey is mandatory for any FW installation. So our FW controllers, we're going to talk about a little bit more here in a second. So they've been out for, going on 2 years now. And we've had, I'm not going to even lie, we've had complaints about them. Wi-Fi signals dropping in and out, so on and so forth. Okay, I get it. Has a site survey been done? That's my first question always. If the answer is no, then I say you got to do it. You got to tell me if there's something blocking the way. You got to tell me if there's some other type of interference. Maybe you're trying to put this on a building that's got a lot of industrial motors, that's putting off some EMF. That Wi-Fi was never going to work. Whether it's our controllers or anything, Wi-Fi doesn't work in this environment. So please, going back, site survey, it's mandatory, guys. You have to do it so you know what your environment is, okay? So, again, if that's something that you don't want to jump into, that's fine. Sub somebody out to do it for you. All right, so let's talk one thing that a lot of people don't think about is power quality. So everybody just installs these cheap little $40 transformers, and then they power it up, and the secondary is grounded, and you power a controller, and now all of a sudden you have crappy communications. Well, guess what? It's not necessarily the controller. When you start implementing, when you start putting noise from bad power quality into a controller that communicates Wi-Fi or wireless, guess what's going to happen? That wireless signal is going to be the one that gets hurt the most, the fastest, okay? So power quality is a big deal. Now, grounding transformers is part of the NEC if a controller or a device comes with a pre-mounted transformer. So they ground the secondary of the transformer. Typically, that's no problem unless the building has grounding problems. Because if the building has grounding problems, then instead of that noise that's being generated from compressors and fans and variable frequency drives and blah, 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 instead of it going to ground, what happens is it can't get to ground. So it goes to the metal casing of the device, rooftop unit, VAV box, whatever, and then it goes into that, back up from that chassis to the ground wire, to the transformer, from the transformer to the controller. And now you have tons and tons of problems, okay? So power quality is a big deal. So make sure you have good power. There are power quality meters. The easiest way to do it, quite honestly, is just to put in some type of a DC switching power supply. That way you don't even have to worry about doing the power. You basically isolate your power altogether, and you don't have to worry about it. But it depends on which way you want to go, okay? All right, so that's the conceptual stuff, guys. So let's talk about our controllers now. So EasyIO came out with these FW series controllers. We currently on the market have 3 of them. We have the FW8, the FW8V as in Victor, and the FW14. The 8 and the 8V are essentially the exact same controller, except the V as in Victor has a pressure sensor, an onboard pressure sensor that could be used for like VAV boxes or something along those lines. Specifications all off to the left-hand side. I'm not going to read through all of them. Essentially, what we did with our FW series is we built I/O around a access point, or a Wi-Fi router is essentially what we've done. So these controllers have the capabilities of a Wi-Fi router being both an access point, meaning that it can serve as the brain on the network to where I can have other devices connect to it, or I can be set up as a client or a repeater mode, meaning that I can take this controller and connect to my customer's network. Okay, either or. Can't do both. I can do either or though. Okay. 2 network ports on the bottom. The network ports, the NICs, Ethernet ports, are not bridged, meaning that if power goes out, it will not communicate across. We do that purposefully. We do that because we don't know what the physical installation is going to be. So if based off of Cat 5, Cat 6 standards, you can run an Ethernet cable 100 meters or approximately 300 foot. So if I run 300 foot to one controller and then out of that controller another 300 foot, if I happen to bridge that controller and that power goes down, and now I have an Ethernet cable that is 600 foot long. And guess what? Oh, my network doesn't work. Well, yeah, no kidding, because you're not dealing with specifications. Okay? So we do that purposefully. So these are just like all of our other controllers, Sedona-based, real-time programming, or live programming as we like to call it. Time clock, SQL database built into them, dashboard graphics. These are BACnet IP servers, and they're BACnet IP MSTP clients, meaning that I cannot take this controller and pass out the data that I created inside of it. I can't push that out BACnet MSTP. Okay, I can only port other devices in BACnet MSTP. The idea behind it is these are supposed to be unitary style controllers, so I install one on a rooftop unit that may have some variable frequency drives. I can take those frequency drives into this controller via BACnet MSTP, and then I can communicate all that data back out to something else via BACnet IP. Okay, so MSTP client, IP client, 5 devices total. IP server means I can take my data that I created in my control program, I can pass that out BACnet IP only, okay? All right. Last thing on that list down there is we do have an FW28 coming soon. So I know Brody will be getting one of these if they don't already have one for beta testing. So we're basically going to put out beta testing, test it, and then we'll have that out here hopefully within the next month or 2 for live for everybody. So essentially what we did is we listened to our customers. Our customer says, hey, we need more points. Specifically, we need more DOs. So if you look at our FW14 and our FW8s have no DOs at all. Our FW14 has 2 DOs, and our customer said we need more. So we came out with the FW28. As you can see, 16 universal inputs, 8 digital outputs, and 4 analog outputs. So really, really great controller. Tons of I/O capabilities, plus it's going to be Wi-Fi. So should be a pretty nice solution. Okay, this is a blow-up version of what the FW looks like. When you actually look at it, just different ways to communicate with it. You got your inputs, your outputs. You got BACnet IP server client. Via Wi-Fi as well as via Ethernet, and then you have BACnet MSTP client only, okay? And this is our FW14 controller that we're showing. All right, so let's talk about this real quick, and then we'll get into some network architecture to finish out. Network security. So network security is a big driving factor in our industry, is this whole IP convergence that I talked about. So get the IT admin involved early. Like I said, quote unquote, befriend them. At least don't become their enemy. Okay, so talk with them. Say, hey, we're looking at implementing this type of solution. Do you have some standards we need to kind of worry about or deal with? So our controllers, they are currently WPA2 AES encrypted protocol. for authentication. We do TLS 1.2. That's for the encryption of the communication across the wire. So if you want to use that with TLS certificates and all that, you can absolutely do that. We have the ability to enable and disable web services. Now, what do I mean by that? I mean, if you don't want to have FTP, SFTP, SSH, HTTP, you have the ability to disable all of that stuff. So there are certain installations where they say, hey, we only want HTTPS, nothing else available. So you can actually disable all of that. Okay, WPA Enterprise will be coming out very soon. WPA Enterprise is a node-to-node authentication. So basically, this controller connects to this server and says, yes, I'm allowed to talk on the network. Once that gives that handshake, then I can now connect to the network and be able to authenticate and do all that stuff like I would normally do. We're still planning on doing a self-healing mesh with this coming later in the year as well. So that will kind of help out with the whole redundancy and all that type of piece from the Wi-Fi standpoint. And then part of that is we also have 802.1x. 802.1x is essentially the same thing as WPA Enterprise, but from a hard-wired connection. So when I plug in, it becomes 802.1x. That's that node-to-node authentication. If I do it wireless, it's WPA Enterprise. Okay, so get with the IT administrator. That's the way. That's the key thing. Key takeaway from that. Okay. All right. So we're going to blast through some network design here real quick because I know we're kind of coming up on time. So we'll run through this. Do it right or you'll do it again. So for the customers on the line, my suggestion is if you're doing an FW installation, get Brody involved. Brody will get us involved if they feel like they want to, and we'll talk about it all together to make sure the architecture is what we expect it to be. Okay? I'm not going to go through all these really slow. I'm going to blast through them. Single site, basically you have an FW. We have an FS controller as kind of our quote-unquote front end where you can do graphics, but you got some FWs doing some stuff, gets it onto the IP network, FWs pulling in some other stuff, and then now you can create a graphic, and it's just a single site solution. Very simple, very effective. Okay? In this scenario, we basically created our own network, so you have some type of a supervisor system. I don't care if that's Niagara, I don't care if it's an FS32 or something else, it doesn't matter. Basically, I have a PC or something sitting there. I run an Ethernet cable from that to one of my FW controllers, which is set up as an AP, meaning that it can do all the DHCP addressing, it can do all the routing and all that stuff. And then you can also take these FW controllers and connect back to that AP via Wi-Fi. Now, we're going to talk about limitations here in a second, okay? All right, so that's this solution right here. This one, very similar solution, except at this point we're doing Wi-Fi daisy chaining. So again, we'll talk about limitations in a little bit, but be very hesitant about doing too many Wi-Fi daisy chaining because you have fault tolerances you have to deal with as well as latency. So we'll talk about what that limitation is going to be. All right, moving on to the next one. So in this one, we basically have Ethernet daisy chaining. So same type of idea, supervisor of some type hardwired directly to one of our FW controllers, out of the FW going to the next, out of that one going next, just like a standard daisy chain. There are limitations on daisy chaining. Again, we'll talk about that in a second, okay? This is no customer network. This is us creating our own network here, okay? All right. Now, let's say, now we got a customer's network of some point. So same type of idea. You got your supervisor system connected to a customer's network, and then we are connected to the customer's network via a Wi-Fi solution. This is probably the best way to do it. The reason I say that is because you offload all of the network stuff to the customer. You don't have to worry about creating it, understanding it, doing it. You basically say, hey, here's what I'm going to be implementing. Here's what I need. The customer says, cool, here's your stuff, and then you set it up per their specifications. Okay, this is probably best case scenario. All right. Now this one, very similar solution right here, except I call this almost like a hybrid style to where I can communicate via wirelessly to the first FW, and then out of that FW, what I do is I run an Ethernet cable to my next one. Let's say that last FW is in some type of a lead-lined room or whatever, then you can't get a wireless signal. I can actually run an Ethernet cable and do that. The deal is that network connectivity does not come into the programming of that first FW. Basically, all it's doing is making a network connection. Okay? So once I get connected to the network, then it doesn't matter. All right? And then same type of scenario here, except I'm using some Ethernet stuff. So
no problem. I can go Wi-Fi, I can go Ethernet, hardwired, daisy chain, so on and so forth. So this is a similar style solution right here, where you have an Ethernet switch coming directly out of the switch. I call this like a spider style or a home run, where you'll go from one controller back to an Ethernet switch. This is kind of the standard when it comes to Ethernet. So if you think about it this way, guys, you're in an office building. Every one of those offices has an Ethernet port on the wall. Those Ethernet ports on the wall all get hardwired back to a network switch. There is no daisy chaining common in the IT world. You're not going to go from one desk to the next desk to the next desk. It all goes back to a network switch. So that's basically this. Okay. Just a couple more things to show here. So basically, in this scenario, I basically have an FW connected to the little green and blue things at the top. That's one of our new controllers called the FT04. The FT04 is connected back via Wi-Fi, and then we have one of our ESR or ESI controllers, BACnet room sensors that connect up via the BACnet MSTP. Okay. And very similar style scenario right here, other than we just got rid of the BACnet room sensor, okay? Because maybe we're taking some hardwired connections into the FT04 thermistor or whatever. All right. So let's start talking about a little bit on the maximum amount of devices. So when we talk about Wi-Fi daisy chaining, we talk about a 4-to-1 style solution. So how you get there is up to you, but 4 connected devices back to one AP, one of our FW APs, okay? Period. So whether this becomes a group where I go 4 of them connected directly back to that one FW, or I have it like this where it's actually Wi-Fi daisy chaining, it's a 4-to-1 solution, period. I will tell you, try not to do it at all. And the reason I say that is because, again, you're going to have latencies, you're going to have fault tolerances. So if that top FW there goes down, then you just lost those controllers that are connected to it. So not the best solution when it comes to implementing a true wireless architecture. But can it be done? Yes. Should it be done? It depends on your application. Okay. Just if you have to do it, make sure you do a 4-to-1. Now I will tell you that typically what happens is people don't do Wi-Fi daisy chaining. What they'll do is Wi-Fi grouping. So in the scenario that we're seeing here, let's say one of those FWs at the top, instead of it being down to the next one, to the next one, to the next one, they'll actually take those 4 at the bottom and they'll connect directly to that top one. So it'll be a group of 4-to-1, not a daisy chain. Okay? So 4-to-1, keep that in mind. When you go to Ethernet daisy chaining, what we talk about here is no more than 9 in a daisy chain link. Okay? So you can actually Google up this and see exactly what there's no real hard limitation on how many controllers and stuff you daisy chain together and back and forth. But we typically like to say no more than 9 for latency and, again, fault tolerances. Okay, so just kind of keep that in your mind, guys. I'm going to buzz through this directional stuff as far as how the antenna pattern works. So when you look at this, basically the antennas, what it does, they come out almost like a donut. So they're not directional. So people like to point the antennas at each other, kind of like this right here. That's the worst thing you can do because the signal off the antennas actually come out like a donut. Okay, so that's definitely not something you want to do. So they're omnidirectional. So when you want to do something like this to where the signal strength actually goes and connects up to each other. Okay. All right. So last thing before I open up to questions, there's a new thing out there. There's a big bunch of buzz called RSTP or MRP. So RSTP is spanning tree protocol. The other one is called media redundancy protocol. Essentially what happens with spanning tree is it looks kind of like this. It's basically you're creating a loop is what happens. So you do it via switches. You don't typically do it via nodes, and that's why it's kind of weird for me to even talk about it as a controller manufacturer, but I know there's other manufacturers talking about it, and honestly, it doesn't make a whole lot of sense to me because the core preface of spanning tree and media redundancy is at the switch level, okay? So essentially you make a loop, and then if something happens and something breaks, a network connection, it can't get through for whatever reason, then it goes the alternate path, okay? So let's look at it. So with spanning tree, that's how it looks with MRP or media redundancy. Media redundancy is basically the exact same thing with as spanning tree, except that it recovers quicker. So let's just look at this one a little bit more in depth. So this is essentially the way that it works. MRM is a manager, MRC is a client. So media redundancy manager, media redundancy client. So in the first picture here, the little blue lines are basically saying that's a blocked port. So what happens is it tries to go, let's call it counterclockwise, left to right, all the way down. Okay, so because it's a ring, that blue blocked port does not let that data go back to that first MRM switch. All right, so you don't have a true always active ring. Now, if you look off to the image off to the right, if something happens and that network gets cut, something happens, port goes bad, whatever, the MRM sees that because it can't get through and connect to everything. So it opens up the block port, and now it goes both ways. So basically it's going counterclockwise as well as clockwise to make sure that it connects to everything on the network, okay? Now, here's a different version of the MRP where you can get very, very in-depth by having, basically rings on top of rings on top of rings. So that's just something to kind of talk about because I know it's kind of in the industry right now, guys. Again, I don't see it personally. I think that it's mainly at the switch level, but I wanted to make sure and hit on it at the very end there. That way everybody kind of got our stance on it. Okay. That's all I got. I know I dropped a bunch of stuff on you guys in a little over an hour. So if you have questions, definitely you can feel free to contact us. You can contact good old buddy Frank or anybody there at Brody to help out. They are recording this, so they'll provide access and all that, and that's all I got. So thank you so much. If there's any questions, I think Frank will open it up, but if not, then I hope you guys have a great rest of the week. Frank?
Thanks, Brian. That was very helpful. Yeah, if there's any questions by anybody, I think everybody had themselves muted. Go ahead, and I think we can open this up. No questions. I guess that's good.
I either did really good or really bad, Frank. That's the way I look at it.
And there was a lot of material covered, and it was thorough. It was, I think it was well worth it. But if we don't have any questions, I know usually what we do at the end of whatever our topic is, we also open it up for, just general questions on anything that's been going on the last month or so. So if anybody has anything else, now's the time to talk. And I guess we don't have anything for today, so I guess with that we can wrap this up. We will get this posted up on our bptechcenter.com.
I just figured out how to take myself off mute.
Oh, there you go. All right, Ryan. Absolutely.
I got one. Not letting you off the hook. You mentioned power quality and if it's an issue to just put in a DC power supply. I'm not sure what you're talking about. Is that a solution to power quality issues using DC power?
Well, so DC power is first off, thanks, Ryan. Appreciate the question. Yes, DC power is actually a much cleaner power than AC. So that does help out. So essentially what it boils down to is I always suggest doing a separate DC power supply. So basically you'll power it from either 24 volts or you'll power it from something else. And what happens is it becomes isolated. So the ground noise that typically is getting pushed up through the cheap transformer now gets blocked at that DC power supply. And that switching DC power supply basically cleans it up. So it does help out. Worst case scenario is if you run into power quality issues, put in an isolation transformer. So you can buy just a very cheap little 24 to 24 isolation transformer just to try to get some of that ground noise from kind of backing out into the controller. So we've had problems with power quality, and literally we would say, hey, put in a DC power, or we would send them something, like one of our FG PWRs, and it fixes a problem. So just proves that there's nasty power out there. One thing that we have done from a manufacturer standpoint is that we are increasing the amount of what I call snubbing capabilities for noise. Unfortunately, there's no real test that you can do for power quality. So I mean, all of our controllers they're all certified FCC and blah blah. You know, all the standard ULs and CEs and all that stuff. So we've passed all that, but we're going above and beyond to increase our snubbing capabilities for power quality and noise to kind of help out a little bit.
Cool. Thank you.
Thank you.
Okay, I guess if there are no other questions, we can call this a wrap and until next month. And Brian, I do appreciate your time and effort to put this together for us today.
Absolutely, Frank. Glad to help.
And thanks to everybody else for attending, and we'll talk to you soon.